Good evening, everyone. Welcome to class 3 of Deterministic Network Calculus. Uh, so last class we saw how do we model arrival characteristics using um, cumulative functions and also departure processes using cumulative functions. We saw some properties of cumulative functions such as non-decreasing um, and piecewise continuous and left continuous. We saw the usage of uh, the interval half open intervals to define the cumulative arrivals and departures so that the Chasles equation is satisfied. Uh, yeah, basically these were the things that we saw yesterday. So today we will start again by defining what a server is. So just to remind everyone of the motivation that we're trying to do. So we are trying to formulate our queuing system, a server S, an arrival process a departure process D as a linear system. So we want to find an mathematical system where the following nonlinear process becomes linear. So you can define B as a convolution of beta, where beta is a service curve that can see. Yeah, so now defining a server. So a server S is a subset of C cross C. So C is a set of all cumulative functions, right? Cumulative functions are functions which have these properties and also a0 equal to 0 and maps to only positive integers, right? So basically, server is a set of, we'll have a set of all a1, d1, a2, d2, so on. Here, these are functions, right? Both are functions, a tuple of functions, right? And and they follow a left total relation. So what do we mean by left total relation is uh, a is greater than or equal to d for all values of t belonging to 0 to infinity. For all positive values of t, the arrival will always be greater than d for all values of t. So when we mean total left relation is followed by a tuple by an element of the set S, which is known as a server, uh, we say that point-wise A and D are have the relation that I have just wrote down. So how do we denote this is we denote this as A. When you pass it through a server S, it gives an output D, right? Or you can write it as A comma D belongs to S. Now suppose okay, let us understand what does this uh, define. So if you give an arrival curve, cumulative arrival to server S, then a D is a possible candidate of departure. If this is in the set S. So suppose you have S1 and S2, have A1, D1, A2, D2, right? Here you have A1, D2, A1, D1, A2, D1. So if you have S1 and you have S1 and you have S2, right? So if you give A1 to this, from this relation, it's clear that the only output that you'll get is D. Similarly, if you give A2, it's clear that you'll get D2. For S2, if you give A1, you can get D1 or D2 because both of these are possible for server 2. But if you give S2 to server 2, then you'll only get D1. You'll not get D2 because that combination is not in the second server. So this is how you define a server. All the possible pairs of arrival and departure cumulative functions. Okay. So uh, basically server, you define it as set of all possible arrival and departure cumulative functions. Okay. So now, uh, okay, one remark is if S, the server, is a function, right? Then we say that the server is deterministic. Now, this deterministic has nothing to do with the um, deterministic network calculus part where you find deterministic bounds for uh, arrivals and departures. But we say it if S is a function, then it's deterministic server. If S is not a function, then it is non-deterministic. Right. Okay. So when I say deterministic, what do I mean by that? I mean that given an arrival cumulative, given an arrival cumulative, we can find the departure cumulative. The departure cumulative is known, it is fixed, it is there is only a unique departure cumulative that when you give A1 gives A2. So for example, S1 is a function. So this is a deterministic cell. Right. Okay, next, non-deterministic server. It just means that given A2, there are multiple possibilities of departure cumulatives. This is a non-deterministic server. Okay, so now this is the mathematical model that we are trying to define a server. Now, in real life, what the server could be anything. Like the server could be a single network element, it could be some switch, it could be some router, it could be the whole network itself could be uh, the server, right? You give some arrival cumulative function, you have a black box, it will give you the departure cumulative function. Like the server is the set of all possible arrivals and departure cumulative functions. Right. Now, Okay, let's talk about flow alteration. Flow alteration. So by flow alteration, I basically mean uh, flow compression or any losses in the flow, right? So if A comma D belongs to S, is a server, then D less than or equal to A, right? So the implicit assumption is that the server does not alter the data. So whatever input you're giving to the server, the same output you're getting from the server, but it is in a delayed state. Like when there is a delay, so there is no loss. There is no loss, no delay. Mm, sorry, there is delay. Why will not there be delay? There is no loss, no compression, no transformation, etc. Any compression or expansion that we can model using a scaling function, which we are not yet talking. So we'll come back and show that what does doing these things affect the uh, modeling that we are trying to do now. But for now, we'll work under the assumption that the server does not alter any data. That is an assumption that we are uh, working on, right? Um, and then we have something called as non-determinism of the server. So, so when we try to model real life systems, even if the real life system is really deterministic, there'll always be some randomness or some potential behavior of the real life system which gets into non-deterministic server model. So, and also if you model it in a non-deterministic way, it is a generalization of the deterministic server. So if you model with randomness, that is sufficient to study the deterministic counterpart of the server also. So while modeling, um, we will basically try to um, incorporate all the non-deterministic behaviors of the real life system that we 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 try to model. So this is what we will try to model. Okay. So next coming the main part, delay and memory. Right. Okay. So delay and memory or delay and backlog. Let's call it backlog, not memory. Delay and backlog. So let there be a server S and A and D are cumulative functions such that ASD. So A and D belong to the set S. Okay, so now for t greater than or equal to 0, we'll write DA comma D comma T is the virtual delay. Now, what do I mean by virtual delay? Is a virtual delay that is associated with the flow A. So if you have a flow A, then if a packet had arrived at time t, what is the maximum delay that it would have seen? What is the delay that it would have seen? We don't know if at t So we don't know if a packet has arrived at T, but if a packet would at T, we want to know the delay. Okay. And similarly, we'll define backlog. So this is the delay at time T or virtual delay at time T. Similarly, we define the backlog. BAD is the backlog at time T. So let me write down the formulas for this. So virtual delay given ADT is basically, so this is defined as infimum, right? D belongs to R plus such that AT is less than or equal to DT plus D. So let me explain this a little bit. So this is total number of packets arrived in the interval 0, T. This is open interval, right? So if a packet if a packet if a packet arrived at T plus, right? The amount of packets in the system would be till AT. Okay, now we want to see when is that packet going to go out. The packet that packet is going to go out when the number of departures are the same as the number of arrivals. So we want to find that the more time that the how much longer has it taken after its arrival. So this is the extra time that it has taken for the arrival, where the departures are equal to the arrivals. So basically, departures will always be less than arrivals. It will not be greater than arrivals. So since both of them are continuous cumulative functions, left continuous, there might be discontinuities, but we want to find at what point it is either equal or greater than. Like what is the first point that is equal or greater than the departures? So the basic assumption under all of this is um, this follows FIFO, right? Next is BADT. So this is backlog. So here we have defined virtual delay, and here we are defining backlog. So backlog is very simple. It's dt minus so at time t, how many packets are arrived and how many packets have departed. So just for example, so for example, 5 packets arrived till time t, right? But only 2 packets have been served. What does this imply? This implies that 3 packets are still in the system. And when I say they are in the system, they are in the backlog. So that is the backlog that the system faces. It is simple. Okay, now let's go back to the constant rate server that we modeled yesterday. I hope you remember what a constant rate server is. So you have a server which serves at constant rate. So mm, it serves at R T minus S if S comma T is backlog. So departures S comma T equal to this. A, you have some variable cumulative function R into. Okay. Then what we find out was dt is equal to inf S T AS plus RT minus S, right? AS plus RT minus S. R into T minus S. Basically, we found out this. Okay, so if we know this, then could we try to find the backlog for a constant rate server? Could we try to find the backlog for a constant rate server? So the backlog for a constant rate server would be just AT minus DT, which is equal to AT minus inf 0 less than equal to S less than equal to T AS plus R into T minus S, right? So now what I can do is I can take this AT inside and write this as sup of 0 less than S less than T AT minus AS plus R into T minus S. But we know that AT minus AS is sup 0 less than equal to S less than equal to T A T comma S minus plus. So now we see that. So this is backlog B T A D E, right? This is for a constant rate server. So what do we see that the backlog for the constant rate server depends on the arrival cumulative function and description of server. Now here when I mean description of server, I mean it is the constant rate server. Could we generalize it more? That is the question. But for now, we are just like uh, going through the basics. So we defined what a constant rate server was. What are the mathematical notions between the arrival and the server characterization so that you get a departure characterization. Then we wanted to find some performance analysis metric from it. The performance metric that we have found out is for the backlog. So how much backlog at time t does it see? Does a constant rate server see? Right. Okay. So next we want to define something known as the worst case delay and backlog. So let us be a server and A and D belongs to us. So you have the pair of arrival and departure cumulative functions. The worst case delay and backlog. So they are given by D, A, comma D. Because it's the worst case, it doesn't depend on time, at what time you're saying it, right? So this is defined as supremum over all T, the set D, A, comma D, comma T. So similarly, backlog, supremum over all T, EA comma D comma D. This intuitively makes sense. So this is for a server and a pair, AD pair in the server. Suppose you don't have that AD pair, you just have the server and the arrival cumulative function. Then what you do? So worst case delay and backlog for arrival. So this is an arrival cumulative function and the server S, right? So DAS, this is defined as sup over set all the AD pairs that are in the server. So all the AD pairs that are, so this is the all AD pairs in the server. You find the um, worst delay, right? Similarly, the worst case backlog is sup over BAD, such that AS. So you need to calculate these to find this. So basically, these are useful. Uh, these are useful if the server is non-deterministic. So what do I mean by that? Suppose you have a server which is non-deterministic, you give an arrival cumulative function. You'll see that there are many possible departure cumulative functions. So to find the worst case, you take among all the possible departure cumulative functions for the given arrival functions of the server, you find the maximum delay that the AD pair sees, right? If it is deterministic server, then given a cumulative arrival function, you'll always know what the departure cumulative function is. Server is non-deterministic. If it is deterministic, then both of them are the same, right? So basically what happens is delays and backlogs at time t. So these two functions at time t, these, they can be interpreted as deviations between A and D. So this is the vertical deviation. This is the horizontal deviation. So now instead of specifying an arrival cumulative function and a departure cumulative function, you can just specify, you can just define uh, vertical and horizontal deviation for all possible functions or some class of functions. Okay, just to make it easy, so instead of depending on all the arrival cumulative function, departure cumulative function, what we'll do is we'll define some functions. Okay, so we have two functions, f and g are two functions which are defined on R plus. Right. So vertical deviation of fg at time, this is defined as ft minus gt. the vertical deviation. So what does this mean is if you have a function f, this is f of t, and if you have a function g of t, okay. So suppose this is t prime, the point at which you want to calculate the uh, vertical deviation. So this is the vertical deviation, right? So the vertical deviation is always calculated from ft. So it will be ft minus gt. That is how it is defined, right? If gt would be below, then the vertical deviation would be this. This would be positive deviation, and this would be negative deviation. Okay. I hope the vertical deviation part is clear. Next is this is vertical deviation at time t. Now you have vertical deviation, just the vertical deviation. So this will give you sup over t belongs to r plus such that ft minus gt. So you take all the vertical deviations that is possible and take set of all the vertical deviations and take a sup among all these vertical deviations. You'll get the maximum vertical deviation between the two functions f and g. Similarly, you have horizontal deviation at time t. This is defined as so suppose you have function ft and you have function gt. So you want to find the vertical deviation of the horizontal deviation of ft at time t prime from here. So the vertical horizontal deviation is this, right? So how do you mathematically define it is, it is the first point after t prime, right? Where gt plus some time hits the exact value that ft has at t prime. So if you want to find the horizontal deviation, so if I want to find the horizontal deviation at t prime, right? Then this is the mathematical formula and the so horizontal deviation, maximum horizontal deviation. You basically have sup over t belongs to r plus and h def over all t. Similar to the maximum vertical deviation, you calculate all the possible horizontal deviations. You write them as a set and you take a supremum over. This will give you the maximum horizontal deviation. So these two are your vertical deviations, which are similar to the backlog that you want to calculate in your real-time system. These two are the horizontal deviations where you want to calculate the delays of the system. So basically what you have is delay ADT is horizontal deviation ADT. Delay AD is horizontal deviation AD. These are delayed functions. Backlog BADT is vertical deviation ADT. backlog AD, maximum backlog is vertical deviation AD. So I have used the term virtual delay, but I have not like clearly said what a virtual delay is, or what do you mean by virtual delay. So virtual delay is basically uh, if a packet would have arrived at time t, then what is the delay that it would have seen? We don't know whether a packet has arrived or not, or some uh, or a packet is arriving in the midway, or it is some instantaneous jump, or we don't know that. Because we are dealing with cumulative functions, we only just see how much uh, data has arrived, but not what type of data has arrived. So when we try to calculate the virtual delay, we see that what if a packet would have come at that time t, then what is the delay that it would have seen here. Okay, so this completes the mm, one chapter on basic modeling of variables and servers, and also the upper bounds. So what we have done now is we have done uh, modeling the variable functions using cumulative functions, and also we have talked about variable curves, which is a bound on the cumulative variable functions. Similarly, we have also uh, talked about server properties. So how do we define a server? So define a basically set of all the possible arrival and departure cumulative functions that we see. Then we talked about some performance metrics, which are delay and backlog. We saw how to calculate delay and backlog for constant servers. We found some good closed form solutions. Mm, So yeah, let me summarize this. So what is the system that we were trying to model, and what is the model that we gave, and what are the math properties it had? Right, system, model, and math properties. So the system is, we first try to model the data flow. So this is cumulative functions. So you have 80 amount of data arrived in the interval 0 to t. We have discussed about this. So what properties does it have? The cumulative functions belongs to a set of the cumulative functions, and a0 equal to 0, right? This is non-decreasing, piece left continuous and piecewise continuous, right? This is what we have seen. Next, we try to server. So how did we define a server? It is basically a relation. We'll talk about this later, between arrival and departure functions, cumulative functions, right? So A and D, relation between A and D, such that you have a set of these tuples where the relation is A is less than or equal, A is greater than or equal to D, and AD pair. The property is left total relation. So pointwise, A is greater than or equal to D. Okay, next we looked at backlog at time t for a flow in the server. So we saw that the backlog is basically the vertical deviation at t. You have maximal vertical deviation, and you have if you and for all possible departure cumulative functions. So what am I talking here are three different things. So the first thing is AT minus DT, the vertical deviation, given an arrival cumulative function and a departure cumulative function, right? Next is maximum possible cumulative, maximum possible backlog, right? This is the maximal vertical delay. And then if you don't know what the departure cumulative is, but you know the server, then you're basically supreming over all the possible mm, departure cumulative functions for a given arrival cumulative function, right? We saw about this. In the same way, we saw about delay at time t for a flow in the server. So here we had horizontal deviation, maximum horizontal deviation, and all possible departure cumulative functions for all those we saw. So similarly, again for the backlog, same thing. Here we have inf d such that at less than or equal to d e plus d, right? The next is supremum over all these. And the next is supremum over all the possible departure cumulative functions given an arrival cumulative function. So basically, this is the summary of what we have seen till now. So you have a system, you have the mathematical model compared to it, and what are the properties that it has. Okay. Uh, yeah. So next, okay, I'll give a basic introduction on what I'll do in the next class. But so yeah, so the next class we'll start with the topic, the min plus functions semi-ring. So we so in the previous classes, what we saw was the minimum and the plus operator, these both operators, appear naturally while modeling any network element. We saw it for concentrate server. So what was the concentrate server? The departure process was basically q of 0 less than s less than t, a s plus r into t minus s. So you saw the min function, you saw the plus operator. So this is basically known as the min plus convolution. We have not yet defined it formally, but we'll go through what the min plus convolution is in this chapter. So basically, the main mathematical backbone of network calculus is the min plus semi-ring. We'll talk what a semi-ring is and all, but I'm just letting you know the terms that we'll be using. So this is also known as a tropical semi-ring. So in the last class, we also saw that the arrivals and the departures of a network. These were modeled by a cumulative function, right? And they were non-decreasing. So any cumulative processes which are non-decreasing functions of time, these can be endowed with the mean plus convolution to form the summary. This we'll see in next class, but um, so basically first we'll define what a dioid is. And we'll also define all the operators that you can function on the diode. So diode and operators will give you the min plus semi-ring properties there, and all these operators, one of the operator would be the min plus convolution, right? Next, we'll discuss about other operators such as sub-additive closures and deconvolution operators. So in these operators, we'll discuss about convolution and also something known as clean star operator. We'll also look into something known as residuation theory. Okay, then this will start in the next class. Next class, we'll start with the min plus based diodes, the min plus based diodes. Thank you for attending the class. I will stop the recording.